everyone, I'm Jason Van Valkenburg from Fungible, and I'm here to talk about disaggregated data centers, some of the challenges and opportunities that disaggregated data centers present in composable disaggregated infrastructure. So we'll talk, what's our agenda? We'll talk a little about just introducing Fungible real quick. We're going to talk about the state of the data center today, the pressures that data centers are under, the case for disaggregation to relieve those pressures, and our approach to delivering a disaggregated data center. We want you to understand some of the common problems in modern data centers today and how composable infrastructure addresses that. And then we'll use Fungible's approach as an example. A real quick shout out to our colleague Jay Menon, our chief scientist at Fungible. We'll want you to take a look at his presentation about computational storage. I really recommend that you check it out because you'll find it quite interesting. Real quick about Fungible, we've been founded by Pradeep Sindhu, the co-founder or the founder of Juniper Networks, and Bertrand Serlet, longtime Apple engineering executive. You know, our purpose is to change the economics, the agility, the security, performance of data centers, right? And we do all of this with a combination of silicon, software, and systems. And you know, we do so with a top class team and have top line backers as well. So what's the bottom line that we want to talk about? Well, first, data center architectures need to transform just as applications have. The mismatch between the evolution that's happening at the application layer that hasn't happened into the data center layer is an impedance mismatch. And the net effect is low efficiency, over provisioning, and excess cost. Yeah, composable disaggregated infrastructure is the path forward, but CDI must not come at the expense of performance, security, or costs. There's prerequisites for successful CDI, and we're going to want to talk about that. And really the net effect is this can only happen with new purpose-built combinations of silicon, software, and systems. So let's first talk about data centers and the situation around data centers today. They're under pressure, right? Software architectures have changed, but data center architectures have not. You know, we've moved to cloud-native applications, scale out versus scale up, microservices, right? All this means is that, you know, there's a lot of chatty applications on the network. There's an increase in east-west traffic patterns. And as your deployment domain, as your data center is scaling out, you know, you're seeing more network congestion and concerns about how do I deliver consistent performance as the data center scales. The other thing that we're seeing is data services like data protection, data reduction, those types of things are starting to move from, you know, dedicated storage arrays. And we're seeing, you know, the prevalence of software-defined storage or hyperconverged infrastructure, right, that are providing things like replication and other things. So the net effect is we have more CPUs being spent on storage. We also have more things going in and out of the network, right? More packets arriving at a server in the form of either work for the network or work for storage, and so forth and so on, right? So there's a CPU tax going on in terms of feeding the beast, if you will, of storage and networking. The relationship between CPUs and IO has changed, right? We've all thought intellectually as networks and storage as slower than servers and CPUs, right? That's no longer the case. The relationship has changed, right? Networks and storage are now significantly faster than CPUs. And then meanwhile, those CPUs aren't getting much faster, right? And then you've got network speeds increasing. So as I'm trying to take advantage of things like 100 gig Ethernet, I'm using more and more CPU cores to push that through. And that's sort of a CPU tax that I never get back, right? Those are cores that I could use for something else. So what's the net effect, right? I have trouble pushing high speeds out of the network, so I have low network utilization, and I have more and more net resources being used to deliver essentially the same capabilities and same SLAs as the architectures evolve as I've described. Right. So basically you're not getting any further along. You're simply keeping your head above the water. Right. So storage and server utilization is low. Data centers have a lot of excess capacity and they're not running at their peak efficiency. Right. Local NVMe is being used for either booting operating systems or providing guaranteed performance. Right. And the net effect is you're taking, or another aspect of this is you're taking traditional storage and deploying them in smaller domains to be able to minimize the blast radius of the performance profile, you know, solve noisy neighbors, those kinds of issues as it relates to storage. So your storage architecture is constraining how you're managing your data center architecture and your workloads. So the net effect is you've got workload-related silos or platform-related silos, all being backed by different storage domains, right? And the net effect is I have silos that need to be sized for their peak and not average usage. And then that effect is I've got wasted cycles and low server utilization. This all means basically, more, wasted cost and effort, right? So we have, in this move to software-defined storage, we have a lot of trade-offs between durability and performance, right? So I've got local NVMe for high performance, but it may not be durable, right? Or if I make it durable locally, I've got to take a big performance hit. Or I've got remote network or remote software service or software-defined services that give me durability, but they're running in x86, they're not giving me performance, right? So I've got massive amounts of IOPS being provided by NVMe that are being swallowed by software services running on top of that, right? And as I'm deploying applications, I need to make a choice between performance and durability. And I've got to make that choice up front to a large extent, unless I've got to go do a migration. Right. Another aspect of that is security is paramount. It always has been, but we have a lot more attention being spent on it now and a lot of effort now that we have things like side channel attacks and other types of things, right? So the threat vectors have gotten larger, right? Encryption at flight and at rest is now a given, it's table stakes, right? And tenancy and isolation are growing in concern as we look at how businesses and organizations are delivering services either to their internal organization or to external parties, right? So you're deploying mitigations for side channel attacks that are sapping performance. You have the issues of zero trust with hosts, or really you have to trust hosts. And our model is to go to a zero trust model for hosts, right? And you have to choose between security, performance, and cost, right? And you can only pick two. It's the magic triangle, right? Or the three-legged stool. So we talked about the net effect of all of this, right? Wasted assets, wasted time, power, and money, right? And really what it comes down to is these silos exist because there's a lack of trust that you can deliver predictable performance consistently when the deployment domain is the entire data center, right? And we want the deployment domain to be the entire data center because that's how we pool all of our resources and deliver the most benefits. Meanwhile, infrastructure expectations have changed, right? People started with a cloud-first approach to now cloud-best, which is great because now we're not viewing all clouds as equal. Some are good for certain use cases. The other thing is that there's a repatriation trend or a move to bring some workloads back from the public cloud for either performance, security, or compliance reasons, right? And when I do that, I don't want to go back to traditional infrastructure for a couple of reasons. One, some of those people don't exist in my organization anymore, right? Your storage admins, when people have gone to the cloud, have moved on to do other things, right? And then meanwhile, the same side of kind of security and isolation, again, from a tenancy model that you see in the public cloud, I want that back in my own data center. So I really want a cloud experience as I'm repatriating workloads, as I'm bringing things into my own data center. So how do we relieve all of these pressures, right? What's the case for disaggregation, right? So our vision is the disaggregated data center, right? And the disaggregated data center takes all of your resources, GPUs, servers with CPUs and memory, storage in the form of SSDs and hard drives. You pool them, and then you disaggregate them, or I'm sorry, you disaggregate them, and then you compose them back for workloads on demand. And you do that in a multi-tenanted way. And this is our vision for what the modern data center needs to look like. It speaks to a lot of operational benefits and other things that you get as a result of this, right? So you get flexibility. You also get the ability to use fewer numbers of these resources to serve the same constituencies, as you allocate on the fly resources across these pools. I'm sorry, workloads across these pools. So what are some of the composition use cases for this model, right? So one is using diskless servers to eliminate all your local storage and eliminate your costs, right? Get rid of those local NVMEs, go to network, do so without using something like Pixie or something like that makes you make special accommodations in the operating system and how you deploy your workloads, right? Should be transparent and invisible, right? But get rid of local storage, put it on the network, put it in the fabric, right? The other thing is we want to be able to do on-demand pooling of GPUs and FPGAs to accelerate AI/ML deployments, right? So GPUs are a constrained resource, both from a logistics perspective right now, but also from a cost perspective, right? And we want to be able to unlock these expensive assets and share them across the data center, right? The other thing we want to be able to do is game the system a little bit by being able to really skew the GPU to CPU ratio in specific use cases, like being able to attach a lot of GPUs to a single host, right? And then we talked about sort of infrastructure, moving to a cloud-like consumption model, or either a cloud operating model, where we're talking about, bare metal as a service or infrastructure as a service to automate and delegate all of your workload deployments, right? So we want infrastructure folks to get out of the delivery chain for IT services, right? And we want to focus on other things. And we want to provide resources to our tenants or our customers, let them run, right? And then we want to have network flexibility and isolation, right? So people, tenants want to be able to create their own networks and have flexibility in terms of how they craft their own interconnects. But we as data center operators want to know that that's being done in a controlled, secure, and safe manner. Right. So what's composition all about? It's really about making immutable hardware mutable and flexible. Right. So we're talking about taking servers, the traditional model with immutable hardware is like that, servers with CPU, memory, disk, GPUs, right? And how I make that experience pseudo mutable is I run something like a hypervisor on top, right? And I basically spread out my control plane across all of these servers, and I basically take the workload and I bring it to the server. Right. So I'm saying, hey, I need a GPU, go find a server with a GPU, run my workload on it. Right. That's being done by something like a traditional hypervisor today. But there are some composable solutions out there that are starting to address this problem using custom interconnects, whether we're talking about PCIe switching or other kinds of technologies. And that's giving us some composition at a device level, right? And that has some benefits, right? I can swap out failed devices. I can take devices and put them in a common chassis where I can treat them specially, and I can do this, remotely. So if I've got a failed device, I can sort of kind of, make a change without having to go dispatch a tech, right? So there's some benefits there, but they're largely bounded by scale of PCI switching in terms of either number of devices or distance, right? So what we want to do is composition at hyperscale, right? We want to use standard Ethernet to do this, and we'll talk a little bit about why later. And we want to be able to basically make a sea of storage appear local to our devices, to our servers. We want to be able to take GPUs off the network and present them locally to hosts. And we want to compose on the fly, and instead of taking the workload and bringing it to the GPU, for example, we want to take the GPU and bring it to the workload. Right. And that model has, in specific use cases, a lot of economic and operational benefits, in addition to just benefits to the workload in terms of performance. So what are the effects of scalable disaggregation and composition, right? And I'm mentioning scalable because I'm meaning, beyond a rack scale. Well, obviously, we're talking about no screwdrivers for adds, moves, and changes. That's a given, right? But what we're really talking about is once you're able to pool these resources and you're able to drive a certain amount of dynamism in terms of how you allocate them and shift resources around in your data center, you're able to use fewer assets to serve the same workload, right? You're thin provisioning storage and then not having to use as much in terms of addressing that local NVMe problem. Servers become interchangeable, right? Disposable, right? So all I have to do is manage the dimensions of CPU and memory, right? And it's interesting is as I have to only manage those two dimensions of servers, it really relieves a pressure, which is having line of sight on future requirements. I can't tell you how many times we've talked to customers and we talk about what are your requirements? Like, what's your workload going to look like in 6 months, 12 months, 18 months? And the answer we get is a lot of blank stares and some ambiguity or some hemming and hawing, right? And we particularly see this in the telco world with the advance of 5G, right? So there's innovation happening, say, for example, in rolling out and deploying 5G, but we know that there's value-added services that are going to run on top of that haven't really yet emerged yet. And so there's a lot of ambiguity as to what workloads are going to look like, and composable infrastructure is a way to address that, right? The other aspect of this is we want to get away from forklift upgrades, right? If I'm pulling storage, GPUs, and CPUs or servers all separate. One of the things I'm doing is I'm allowing them to have different life cycles, right? So if you think about the life of a server now with the plateau in performance, servers are going to last a long time, right? I can leave them in service for an extended period of time. GPUs may actually have a shorter finite life, more finite lifespan, right? There's additional innovation going there. There's also a lot of pressure on GPU performance from the standpoint of AI ML models getting larger and things like that, right? And storage is obviously always an area of continual evolution, right? So now I can manage these pools not only individually from a deployment perspective, I can also manage them independently from a lifecycle perspective. And the other aspect of that is just heating, power, cooling, right? Disaggregation lets me take things like hot GPUs and put them in a colder spot, right? There are benefits to that versus spreading out hot GPUs across the entire data center, especially when you look at locales and parts of the world where power and cooling is a strain and a stress and a finite resource altogether, right? So there's a bunch of benefits, and I'm sure that as we all know, there's more here as well, right? So what are the prerequisites for successful disaggregation, right? We say this is the path forward. What do I need to get there? Well, so first, people aren't going to be willing to disaggregate if it comes at the expense of performance and usability, utility, right? So, we want our cake and eat it too, and we're not going to be willing to give up, things like performance, because in many cases, those are the very reasons we are still running our own data centers today, unless I'm a service provider, right? So, performance and usability is paramount. It's got to be invisible to the workload, right? And this is the context of this is who's consuming IT services today and who is providing IT services, infrastructure services, are different, right? So, we're moving now to people like DevOps consuming, people driving workload deployments versus infrastructure folks or app admins, deploying applications, right? So what this means is that the disaggregation architecture has to be transparent, it has to be invisible, or it has to be at least deployed in a way that makes you not have to make special accommodations or do anything special, right? We want to prevent what I call fabric fatigue, right? So there's a skill shortage, right? As people have moved to the cloud, finding traditional infrastructure skills is becoming more of a challenge in certain markets. And adding another fabric, right? Like adding another kind of technology into the mix, right? Adds to the fatigue there, right? And everybody's got their own physical way of doing this. So we want to be able to take advantage of the equipment, techniques, and knowledge that you already have in your organization and the investments that you've already made. So what this means is I need high-speed storage without scale and deployment constraints, right? So if I'm going to disaggregate, it's got to be fast, and I need to be able to continue to scale it and not take a hit on that. We need a low latency, congestion-free Ethernet fabric, right? So not a different kind of fabric. It's the fabric you already have, right? Use the equipment, the vendors, everything that you have today for your network, right? But the network needs to be low latency and congestion-free, and not all Ethernet networks, have those characteristics in spades. And we'll talk a little bit about how we address that in a moment. All right, and the workload needs to, again, not have any kind of special accommodation. So we want bare metal without any kind of special host software, right? We want people to just inherently use the machine, use the equipment as if it's just a normal server, right? There should be no difference or no discernible difference that the fact that the infrastructure is disaggregated. So really, successful disaggregation comes down to scalability, network, and ease of use and ease of deployment, right? So let's drill down a little bit on some of those. So our answer to, let me take a step back, our answer to these challenges, right, and is our DPU, right? And we take some pride in having created the term DPU, and it's become, more widely deployed in the industry. The key thing here is we think of it as the third socket, and it is optimized for data-centric operations, right? And what that means is, data is coming to a server in a packet, leaving in a packet, right? So we need to be able to address how that model is working, accelerate it, and free the CPUs from having to do these types of tasks and operations, right? So the DPU and the fungible DPU is key to that. We just have two kinds of DPUs, two form factors at the moment. We have an 800 gig F1 DPU that is the backer for our storage platform, right? So it's the backer for the storage product, which I'll tell you a little bit about. And then we have a 200 gig S1 chip, which is designed to go in hosts to accelerate and offload CPU processing in traditional servers. Right. So what our DPU is about is it's a unique mix of silicon and software, right? So these are a lot of bullet points here that are gonna I'm not gonna go through these in any kind of depth, but the key takeaway that I want you to have is that we have purpose-built this chip for its use case. We have, and we match it with software called our Composer, which handles things like configuration, monitoring, telemetry. So we have a chip that has a data plane on it that handles all of the data processing. We have a control plane that manages that data plane that's on the chip as well. And then we have a composer layer of software that manages higher level concerns. This layering and also the separation of data plane from control plane and the layering of additional control planes on top of each other is really the special sauce for how we continue to innovate and how the solution scales linearly, when it's deployed. So what are our GPU powered data center solutions? First, we touched on a little bit. We have a fungible storage cluster, which is a cloud scale all NVMe device, which is designed to really give you no compromise features in terms of performance, durability, protection, all those types of things. We have function accelerator cards that sit in hosts that offload storage and networking from the CPU, right? And the idea there, just like any other accelerator card, is we're taking load off the CPU and accelerating things. Now, by having a GPU in our storage cluster and a GPU in our card, there's some special things that we can do that I'm going to touch on in a moment. And then, of course, we have software to manage it all, and the ability to really turn these piece parts into a turnkey, multi-center data center deployment, right? So this software then has the ability to manage not only the storage and the compute cards, but also servers and compute as well, and meld them all together into a cohesive cloud experience. Some of the benefits are for storage cluster, right? It's going to come down to pooling, performance, supporting VMs, scale out, tenancy, a lot of different kind of bullet point types of things. And I'm trying to move through this a little quickly, but the key thing that you want to know is fast, cost effective, and you can start small and scale out, right? Without having to re-architect or rip and replace. And we do so with all of the other kinds of considerations that we've talked about, right? So lots of features, lots of benefits, right? We use a scale out architecture. So we talked about the separation of a management and control plane from the data plane. Our storage arrays really are focused on data movement, right? And then we have a Composer x86 software level, which is handling higher level concerns like placement, triggering recovery, discovery, providing the APIs. And so by separating out the control plane from the data plane, we're able to scale out the data plane non-interruptively. We're able to do software updates of the higher level functions without interrupting the data plane, right? And so we've got a lot of operational benefits that convey. And the idea here is this is the key and the special sauce to cloud scale and scale out architecture, right? So have the ability to go big without having to worry about your lockstep growth along the way. So another aspect of that is we have a hierarchical control API, hierarchical API approach, right? So we've got APIs that are running on our storage arrays. We've got APIs that are running on our storage controller, right? And then you've got workloads like OpenStack or Kubernetes that are driving, higher level concerns. And this layering of the APIs is essential to providing both, rough-grained and fine-grained capabilities depending upon, your particular use case. But really, what this is about is moving to an intent-based API approach, but having all of the key thing for us is having all of these things layered and controlled so that we can continue to innovate at each layer independently from each other. Under the hood, the only key thing for you, I'd like you to take away today from this is there's no x86 in this device, right? So we're using this purpose-built silicon to drive all of the benefits that we've talked about, right? Looks very, very clean here. I've got, some drives and a GPU, and that's basically it. With this, we're able to deliver some phenomenal performance, right? So we're able to do it both with raw, and then we're able to do it with replication, and we're able to do erasure encoding, 4+2, for example, with phenomenal performance, which means we can do erasure encoding for hot data, right? So when you think about the traditional use cases for erasure encoding, it's often for cool or cold data. And what we're really about is providing, the efficiency of erasure encoding with the performance that you wouldn't otherwise be able to get. Here's some proof points of just some benchmarks that we've running, for example, Oracle RAC. We've protected the names of the innocent in terms of some of the other vendors out there. And obviously, we're using what's available publicly about some of the alternatives. But the key thing is, being able to deliver more performance with less. And in this case, we're using just the straight Linux NVMe or TCP storage initiator, right? So we're not using the model that I talked about, or I will talk about, where we've got GPUs on both sides, right? So the key thing here, higher throughput, fewer x86, cost benefits are phenomenal and through the roof, right? But I've talked about being fast, and being fast does not alone deliver the mail, right? So we want to talk about, if I've got a sports car, it's no fun if I'm stuck in traffic, right? So end-to-end speed is only valuable if you can avoid congestion, and not, throttle back congestion once it's happened, but prevent it from happening, in the first place. And the approaches we use today for congestion control or for really traffic distribution, like ECMP, use hashing, and hashing trigger, is subject to collisions. And particularly in the microservices world, where you've got, really, really predictable interactions between components, right? You essentially have static loading of paths. And then you've got elephant and mice traffic flows that end up resulting in congestion, stuff backing up. And then as soon as congestion happens, how do we correct it from a protocol perspective? TCP is going to go struggle and do all these things, right? So what we really need is a congestion-free experience and network. And we have an answer for that. Ours is a IP over Ethernet based technology called TrueFabric, right? And it's based on open standards, uses standard switches, right? IP over Ethernet, right? But its objective is to provide cross-sectional any-to-any bandwidth with no constraints, right? We do end-to-end congestion control and error control, but we're avoiding congestion in the first place, right? And the net effect is we have the ability to drive high amounts of network utilization with very predictable experience, right? And to do so with encryption built in and all these other, nice things like that. So TrueFabric addresses the traffic lane problem. The DPU addresses the speed problem, and combined, you're able to go, coast to coast in a certain number of hours, right? You're able to really, truly deliver the end-to-end performance that disaggregation needs, right? So with TrueFabric, what do you get? You get a bunch of benefits like efficiency, performance, scalability, security, yada, yada. I'll leave these here for you to take a look at. But the benefit here is by doing what we do in the hardware, right? We're able to really expand that deployment domain, make data locality in the data center a moot point. And the net effect is then I get all the benefits of disaggregation that we've talked about, right? So without this technology, you'll get congestion. You'll end up over provisioning your network, spending more to do the same, right? And so TrueFabric is integral to our special sauce, if you will. The other thing we talk about is multi-tenancy, right? And so tenancy is important, right? Not only if you're a service provider, but if you're a enterprise with business units or what have you, right? Tenancy is just a given, right? I need to be able to address noisy neighbor problems. I need to have isolation, right? And so we take, in our model, you take a tenant and you assign servers, storage in the form of IOPS and capacity, GPUs, and networks, assign them to a tenant, and the tenant's able to go run and deploy workloads as they see fit, right? The key thing that we want here is self-sufficiency. We want the infrastructure folks out of the infrastructure delivery chain, right? Once the infrastructure is set up, let workloads, let project teams, customers, whomever, go deploy workloads as they see fit. right? And provide, all of the nice benefits associated with self-service, portal, separate APIs, so forth and so on, right? The other aspect of this is we talk about, we don't want to go back to how infrastructure was before, right? We want to have that cloud-like agility, but we want to have it on-prem, or we want to have it in our own data center. And so, one of the things that we're really excited about is being able to take things like the automation from the public cloud and things like Cloud Init and deploy that as bare metal, right? So essentially, you have a cloud instance that's bare metal with all of the automation associated with it. So it's very similar to what you would get in a bare, like an Amazon and a Perna, or something like that, from the standpoint of it feels like a cloud instance, it feels like a VM, but it's all bare metal, right? And the idea here is that from a migration perspective, you can take all the automation that you have from the public cloud, drop it into this composable infrastructure, and you're ready to go, right? You don't have to redo all of that infrastructure automation work. The other aspect of that is, being able to have consistent, repeatable application deployments, right? And so, the lesson learned from the cloud, right, is that it's that ease of use, making things easy, matters, right? And so when we think about moving to our own data centers, we want to have the same level of simplicity and the same experience, right? And how we do that is with our one-click marketplace and templating, right? Using things like Cloud Init and disk images, and we're able to basically combine these so that you can share recipes and other types of things, right? Virtualization platforms have these, right? And so that's not revolutionary. But what, the real key takeaway here is that we want to have this same experience of the cloud in bare metal, right? So that we want to be able to repatriate our workloads, not have to repave the cloud skill sets of our people, not get them back into traditional ways of managing infrastructure, and really free them up to do business as they're doing today in the public cloud. Now, to recap, what are the benefits of a fungible data center? And when I mean fungible, I'm really talking about the adjective as much as the noun, right? So, the key thing, as we talked about before, is we got to continue to deliver performance, right? We want to offload data-centric processing from CPUs to the DPU, free up cores for the host. We want to do so with, great power efficiency. We want to do so with security. So, we want to have a non-trusted host. We want to have fine-grained segmentation, quality of service, line rate, and at-rest encryption. All these things that you expect from modern secure infrastructure. We want to do this on the fly. We want to be agile. We want to be able to move resources around, right? That's how we get the multiplexing advantage and the economic benefits of not having to buy as many GPUs, not having to buy as many servers, right? We need to be able to do it simply, because the model today is simple. We want to take complexity and boil it down to a couple of clicks. And the net effects of all of this are, you're managing fewer types of servers. You're having to buy fewer types of servers, and so your resiliency model goes from for each silo n+1 to n+1 for the entire data center, right? Or n+2 or whatever, right? So the thing is that you're buying fewer servers for spikes and spares, right? You're getting higher utilization of those servers, and you're doing all of this just in time. So you don't have to plan too far ahead in terms of what's coming down, down the pike for workloads. So we talk about that ambiguity problem. So that's really, fungible data centers, in a nutshell. And I really want to appreciate and thank you all for listening today. And I hope you have a great day. Thank you.